Imagine you are searching for a single record in a database table containing 10 million rows. Without an index, the database engine has to perform a full table scan, checking every single row one by one. This is O of n complexity, and on modern hardware, reading that much data from disk could take seconds or even minutes. This is where indexing comes in. An index is a separate data structure that allows the database to find rows without looking at every single one. Most people think of an index like the back of a textbook, but the underlying structure is far more sophisticated. In most relational databases, like PostgreSQL or MySQL, that structure is a B tree. Today, we are going to peel back the layers and see how these trees actually organize data on your physical disk to make queries lightning fast. To understand B trees, we first have to understand the hardware. Data isn't stored in a continuous stream on your disk. It's organized into blocks or pages, typically 4 or 8 kilobytes in size. When the database needs data, it doesn't just grab one byte. It fetches an entire page into memory. Disk I/O is the biggest bottleneck in database performance. Moving the mechanical head of an HDD or even the electronic signaling of an SSD is thousands of times slower than CPU operations. Therefore, the primary goal of a B tree is not just to organize data, but to minimize the number of page reads required to find a value. We want a structure that is shallow and wide, ensuring that even with billions of records, we only need to fetch 3 or 4 pages to find what we need. You might be thinking, why not use a standard binary search tree? In a BST, every node has at most 2 children. If you have 1 million records, a balanced binary tree would be about 20 levels deep. That sounds efficient, but remember our disk pages. In a BST, each node would likely live on a different disk page. To find a record, you would have to perform 20 separate disk reads. That is way too slow. B trees solve this by having high fan-out. Instead of 2 children, a single B tree node can have hundreds of children. By packing many keys into a single disk page, we can drastically reduce the height of the tree. A B tree with a fan-out of 100 can store 1 million records in only 3 levels. That's only 3 disk reads instead of 20. Let's look at the internal structure of a B tree node. Each node contains a sorted list of keys and pointers to its children. For example, a node might contain the keys 10, 20, and 30. These keys act as signposts. The first pointer leads to a page with keys less than 10. The second pointer leads to keys between 10 and 20, and so on. This is the multi-way search property. When the database searches for the value 15, it loads this root page, sees that 15 is between 10 and 20, and follows the second pointer. It ignores all other branches of the tree entirely. Because the keys inside a node are sorted, the database can use binary search within the page in memory, which is incredibly fast compared to the disk jump it just performed. One of the most critical rules of a B tree is that it must remain balanced. This means all leaf nodes, the ones at the very bottom that point to the actual data, must be at the exact same depth. When you insert new data, the B tree doesn't just grow downwards like a vine. If a node becomes too full, it splits into 2, and the middle key is pushed up to the parent node. If the root itself splits, the tree grows 1 level higher. This bottom-up growth ensures the tree is always perfectly balanced. This guarantee is why B tree performance is so predictable. Whether you are searching for the very first ID or the very last, the number of disk pages you need to read remains the same. In a real database, like a B+ tree variant, the internal nodes only store keys in pointers, while the leaf nodes store the actual data or pointers to the table rows. These leaf nodes are also linked together in a doubly linked list. This makes range scans incredibly efficient. If you run a query like select star where ID between 10 and 50, the database finds the leaf for 10, then simply follows the horizontal pointers to collect all the subsequent records until it hits 50. It doesn't have to go back up to the root. This combination of vertical traversal for single lookups and horizontal traversal for range scans is why B trees have been the gold standard of database indexing for over 40 years. So next time you write a SQL query and it returns millions of rows in the blink of an eye, remember the B tree. It is a masterpiece of computer science that bridges the gap between high-level data models and the physical reality of spinning disks and flash memory. By using high fan-out to minimize disk jumps, staying perfectly balanced through splits and merges, and allowing for rapid range traversals, B trees ensure that our data remains accessible no matter how large it grows. Understanding these internals helps you write better queries, design better schemas, and ultimately build faster applications. Thanks for watching and happy indexing.